If you're fascinated by the darkest objects in the universe, the places where physics starts to break, then you're in the right channel. Before we begin, hit like, subscribe to WonderDocs, and turn on the bell because this video is part 1 of a series where we explore the biggest mysteries in space, with cinematic storytelling and real science. Now take a breath, because we're about to step into a region of the universe where time bends, light can't escape, and even our best theories start arguing with each other. We're talking about black holes. Most people think black holes are simple, a giant cosmic vacuum that sucks everything in, but that idea is almost completely wrong. Black holes are not just holes, they are objects real, measurable, and unbelievably complex. They are like laboratories built by the universe itself, designed to test the limits of reality. And here's the twist. Black holes aren't only terrifying, they're also revealing, because hidden inside these monsters are clues about the deepest questions we've ever asked. What is time, really? What happens to information? Can gravity be unified with quantum physics? And how did the universe build something so powerful so early tonight? On WonderDocs, we're going to explore the mysteries of black holes, from what they are to what they might be hiding. Let's start with the first mystery. A black hole is defined by a boundary called the event horizon. That's the point of no return. But the event horizon isn't a wall, and it isn't a physical surface. If you were falling toward a black hole, you might not even notice when you crossed it, at least. Not for a large black hole. You wouldn't hit a barrier. You wouldn't feel a sudden impact. So what is it? It's a line in space where the escape velocity equals the speed of light. Beyond that point, even light, the fastest thing in the universe, cannot climb out. And that's the first reason black holes feel like magic. We're used to thinking that light always wins. But around a black hole, light doesn't lose because it's slow, it loses because space and time are warped so strongly that all possible future paths lead inward. That's not poetry, that's geometry. In Einstein's relativity, gravity isn't a pulling force in the usual sense. Gravity is what happens when mass and energy bend the fabric of spacetime. A black hole is what you get when that bending becomes so extreme that the downhill direction points into a region you can never return from. But if the event horizon isn't a surface, then what's inside it? And that's where the universe starts smiling like it knows something we don't. Most of the time, black holes are born when a massive star dies. A star lives in a balance between two powers, gravity pulling inward, and pressure pushing outward from nuclear fusion. But eventually the star runs out of fuel, the pressure weakens, gravity wins, and the star collapses. If it's big enough, the collapse doesn't stop at a white dwarf or a neutron star. It keeps going, compressing matter beyond any state we can recreate on Earth until it forms a black hole. The result is an object that can be described, astonishingly, with just a few numbers: mass, spin, and electric charge. This is called the no-hair idea. It's one of the strangest truths in astrophysics. You can throw in a mountain, a planet, a library, a diamond, or an entire civilization, and once it settles down, the black hole becomes almost indistinguishable from one formed by anything else. Everything you toss in seems to vanish from the outside universe. Which leads to the next mystery. If everything falls in, where does it go? To understand why this is so hard, we need to talk about the center, what relativity predicts is inside. At the heart of a black hole, Einstein's equations point to a place called a singularity. A singularity is where density becomes infinite and the known laws of physics break. It's not just very dense, it's the math stops making sense. But here's the key. Many physicists believe singularities are not real physical objects. They may be a sign that relativity is incomplete, like a warning light on a dashboard, because infinities in physics often mean we are using the wrong theory. So what could be inside instead? Some ideas suggest a singularity might be replaced by a core of ultra-dense quantum matter, a bounce into another region of spacetime, a weird quantum star that never quite becomes infinite, or something even stranger, information stored on the horizon itself. That last idea brings us to one of the most famous puzzles in all of science, the black hole information paradox. Here's the paradox in plain language. Quantum physics says information cannot be destroyed. Information here means the complete description of a system, like what particles it contains, their states, how they are arranged. Even if you scramble something, the information is still in there somewhere, in principle. But black holes seem to destroy information. Imagine you throw an encyclopedia into a black hole. From the outside, you only see the black hole's mass increase slightly. You have no way to recover the contents of the encyclopedia. It's gone. Now, if black holes were eternal, you could argue the information is still inside, just unreachable. But in the 1970s, Stephen Hawking changed everything. He showed that black holes should not last forever. they should evaporate, and the reason is even stranger than the black hole itself. In quantum physics, empty space is not truly empty, it's a restless field of fluctuations. Particles and antiparticles can briefly appear and vanish. Normally they annihilate instantly, leaving no trace, but near the event horizon, something different can happen. A pair appears near the boundary. One falls in, the other escapes. To an outside observer, it looks like radiation is coming from the black hole. This is Hawking radiation. The black hole loses a tiny amount of energy. Over unimaginable timescales, it shrinks. Eventually, it can evaporate completely, and that's where the crisis hits. If the black hole evaporates away, and all you're left with is Hawking radiation, where did the information go? Because Hawking radiation, in the simplest picture, is random, like static. It doesn't carry the detailed story of what fell in, so either information is destroyed which breaks quantum physics, or the information somehow escapes in the radiation which requires subtle hidden structure, or something remains at the end, a remnant holding the information, or our understanding of space-time is missing a deeper rule. This paradox is not a small technical issue. It is a direct clash between the two greatest theories humans have ever created, relativity and quantum mechanics, and black holes are the battlefield. To solve the paradox, physicists have proposed multiple mind-bending possibilities. One idea says the information is actually encoded on the event horizon itself. This connects to something called the holographic principle, the suggestion that the information in a volume of space can be described by information on its boundary. It's like saying the 3D world inside the horizon could be stored on a 2D surface. That sounds insane, until you realize we already see hints of it in black hole thermodynamics. Yes, black holes have thermodynamics, they have temperature, they have entropy, they even follow laws similar to the laws of heat. And here's the shocking part. A black hole's entropy is proportional not to its volume, but to the area of its event horizon. But area scaling is a clue that something deep is going on. The horizon acts like a storage device. If that's true, then Hawking radiation might not be purely random. It might carry hidden correlations, tiny patterns that, over time, could leak out the information. But making that work without breaking other rules leads to new problems, like the firewall paradox. The firewall argument, in simple terms, asks, if information escapes in Hawking radiation, then the event horizon can't be a calm, ordinary region of spacetime. It might be a violent boundary where infalling matter gets destroyed, a firewall. But that creates a conflict with Einstein's relativity. So black holes force us into a painful choice. Keep quantum physics safe, but break Einstein at the horizon. Or keep Einstein at the horizon, but accept strange quantum behavior. And that's why black holes remain mysterious. Every solution demands a sacrifice. Other solutions propose fuzzballs where the interior is replaced by a fuzzy quantum state, or even wormholes connecting the interior to the radiation. Because black holes are the only place where the universe seems to demand a unified theory. Now, while all of that is happening in theory, black holes also present huge mysteries in observation. For most of human history, they were invisible, but that has changed. In 2019, the Event Horizon Telescope revealed an image of a black hole shadow in the galaxy M87, and later, the one at the center of our own galaxy, Sagittarius A*. These aren't photographs of the black hole itself. These are images of hot gas swirling around it, forming a glowing ring. The dark region is the shadow cast by the event horizon. And here comes another mystery. Not all black holes behave the same. Some are quiet, some are violent, launching jets of plasma thousands of light years into space. Around many black holes, matter forms an accretion disk, a whirlpool of hot gas. In some cases, the black hole's rotation can drive these jets, which can shape entire galaxies. So black holes aren't just cosmic vacuum cleaners, they can be cosmic engines. And the environment around them can be the brightest thing in the universe, like quasars, which raises a huge question. How did the universe build supermassive black holes so early? We found them when the universe was less than 1 billion years old, weighing 1 billion times the sun. That's a problem. Standard growth models struggled to produce them that quickly. So what happened? One possibility is that the first stars were massive and collapsed into large seed black holes that grew fast. Another is direct collapse, where a giant cloud of gas collapses straight into a large black hole, skipping the star stage. And then there's a more exotic option, primordial black holes, formed moments after the Big Bang from density fluctuations. The idea remains one of the great what-if mysteries. Now let's talk about another black hole mystery, intermediate mass black holes. We know stellar and supermassive black holes exist, but what about ones in the middle? hundreds to thousands of solar masses. They should exist, but they are hard to detect. Recently, astronomers have found stronger candidates. If they are common, they could be the missing link in black hole growth. And the story continues to evolve because of a new kind of observation: gravitational waves. In 2015, LIGO detected ripples in space-time caused by colliding black holes. It was like the universe handed us a new sense. When two black holes merge, they release energy in waves. These signals have taught us that black holes can be heavier than expected and form in different environments. We are now building a catalog of black hole mergers, and each one is a clue. But one mystery remains the most haunting. What happens to you if you fall into a black hole? Near a smaller one, tidal forces would stretch you apart. But near a supermassive one, the tidal forces at the horizon are much gentler. You might cross it without noticing, but once inside, every path leads inward. Inside the horizon, the direction toward the center behaves like a direction in time. You can't stop moving toward it any more than you can stop moving into tomorrow. We don't know what happens, and that we don't know is the reason black holes are so important. They mark the boundary of human understanding. So what are the biggest black hole mysteries? The nature of the interior, the fate of information, the origin of supermassive black holes, the true behavior of space-time at the horizon, and their role in shaping galaxies. And perhaps the greatest mystery is that black holes might be the key to a deeper theory uniting gravity and quantum physics. Let's end with a thought. Black holes are often described as destroyers, but they are also creators. They create jets, gravitational waves, and questions that push science forward. They are the universe's greatest tests, and new telescopes are helping us crack these mysteries. But the deeper we look, the more the universe seems to whisper. You have only just begun. If you enjoyed this journey, subscribe to Wonder Docs, leave a like, and comment below which black hole mystery is the most mind-blowing: the information paradox, the singularity, or the origin of supermassive black holes. And tell me what you want us to explore next: wormholes, dark matter, or the scariest things James Webb has ever found. Until the next voyage. This is Wonder Docs staring into the darkness, so we can understand the light.